2.1, idea of limits. Essential earnings are average rate of change versus instantaneous rate of change, slope of the secant versus slope of the tangent, and what happens to the secant as 2 points on the curve get very close together. So let's answer a couple of these questions real quick. Say I have a curve on a sketch. I'll use this more formal sketch in a moment, but say I have this function y equals x squared, and I find the secant line between these 2 points. What happens as this second point converges on that first point? Well, what happens is that secant line now becomes a tangent line. So this idea of average rate of change is the idea of a secant line, right? It would be the slope of the secant line. And instantaneous rate of change would be the slope of the tangent line. Well, I wrote tan. Well, I meant tangent, but I wrote tan. Okay, so the slope of a secant line and the slope of a tangent line, they are related to the average rate of change and the instantaneous rate of change. So as the points on a curve get close together, we get this tangent line starts to form. So here's the graph of y equals x squared. A secant line connects the 2 distinct points on a curve. Find the slope of the secant line between the point 1, 1 and 3, 9. Okay, so 1, 1 and 3, 9. Right, to find that slope, we'd take y2 minus y1 over x2 minus x1. So I'd take 9 minus 1 over 3 minus 1, which is 8 over 2, which is 4. Okay, it looks like that matches our work below. All we're doing is calculating the slope of a secant line. Now what they want us to do in the second example is use the same graph, except now we're going to converge and we're going to squeeze the distance between those two and make it smaller. So let's go from 1, 1 to 2, 4. So 1, 1 now to 2, 4. So that'll be y minus y over x minus x, which will be 3 over 1, which is now a slope of 3. So in the second part, part B there, we get the slope of our secant line. Slope of our secant line in the second part will be 3. Now, there's not a nice integer value between there, so we're just going to go to 1.5, 2.25, 1.5, 2.25, and we're going to find the slope between those now, that secant line. So it'll be 2.25 minus 1 over 1.5 minus 1, which would be 1.25 over 0.5, which is 2.5. Okay, so you can see that the slope is going from 4 to 3 to 2.5, approaching some value, right? So the slope of this secant line was 2.5. Let's move on to the next slide and see what happens with this. In general, the slope of the secant line can be calculated using the slope formula with these 2 distinct points. An application of the slope of the secant line can be something such as miles per hour. So suppose you want to calculate your average velocity. This is average velocity, not instantaneous. If you pass milepost 100 at noon and milepost 130 at 12:30, you travel 30 miles in 30 minutes. So your average velocity, the slope of the secant line over that time, would be 30 miles per 1/2 hours, which is 60 miles per hour. Let's move on. Let's talk a little bit more about this general form of the slope of the tangent line. So secant lines from part A and B and C are starting to approach a single line, right, as when x equals 1. So we're converging, right? Our x plus h is starting to converge to just 1, right? So h is starting to turn into 0, right? If we try to calculate the slope of the tangent line at x equals 1 using traditional methods, we'll run into a problem, because what will happen to the denominator? Well, our 2 x values will be the same, and therefore we'll divide by 0 and we'll have an issue. So the slope of the tangent line is called the instantaneous slope at a specific x value. Now what's happening here in the second formula is the slope of the tangent line is our second x value approaching our first x value. Right? So when we looked at this, our first x value is here. Our second x value started to approach that and would then, therefore, eventually, as we'll see in the following examples, will become that, and we'll get the instantaneous rate of change. So let's use this idea of the difference quotient to find out what the instantaneous rate of change would be when x equals 1. Right? You could probably make a hypothesis about this, but I'm going to go ahead and use the difference quotient. So f of x plus h minus f of x over h, I'm going to FOIL that, x squared plus 2xh plus h squared. That's that first expression FOILed out, minus x squared over h. So it looks to me like these x squareds will cancel. I'll get 2xh plus h squared over h. And notice in both of the numerator terms we have an h, therefore an h will cancel out of each of those, and our difference quotient simplifies to 2x plus h. Let's see what happens with that in the next slide. So now we want to use the simplified difference quotient. Let's write it down. The simplified difference quotient was 2x plus h. And we're going to substitute in x equals 1. So we know x equals 1. And what's happening to h? Well, h is going to 0. So we're going to plug those two values in, and let's see what happens with our slope. Right? This is just calculating the slope of that tangent line. Well, it looks like that slope of that tangent line will be 2. Now, let's look at the values that we had before and see if it makes sense. As h gets smaller, right? So we've got larger h's, and as h gets smaller, approaching 0, what happened to our slopes? Well, they went from 4 to 3 to 2.5, and then we took this big jump to 2. So it looks like the slope of our tangent line would be 2. All right, let's use another example here, just kind of algebraically manipulating using that alternate form of the difference quotient, using our function f of x equals 1 over x. So f of x equals 1 over x. F of a would be 1 over a. And x minus a would stay as follows. Now, a method that we like to use here is we like to do what we call clearing the denominator, or clearing fractions. So I want to clear out both of these so I don't have a fraction in the numerator. So I'm going to multiply top and bottom by ax. Okay, so if I multiply this first term, I've got to distribute. So if I multiply that first term times ax, it looks like I'll get a. If I multiply the second term times ax, I think I'll get x. So I get a minus, I get a minus x over ax times x minus a. And there's a little bit more we can do here. You may or may not see it right off the bat, but the numerator can be turned into negative x minus a. We'll put that over ax times x minus a, and something kind of cool happens. We get this simplified difference quotient. So let's go ahead and find the average rate of change from a equals 1/2 to x equals 1. So we're going to take what we know, which is negative 1 over ax represents the difference quotient in that alternate form. A is 1/2, and x is 1. Looks like we're going to get negative 1 over 1/2, which, using this property of fractions, we divide by a fraction, we multiply by its reciprocal. It looks like our slope there would be negative 2. Let's do the same thing here with 3/4. Negative 1 over ax would equal negative 1 over 3/4 times 1, which would equal negative 1 over 3/4, which I believe will be negative 4/3. Let's do it one more time where both x and a equal 1. It is at times advantageous to use this alternate form of the difference quotient because it makes things a little bit simpler on occasion. It looks like that slope would be negative 1. Let's take a quick look at the graph. here's 1 over x. And in this case, we're just looking at positive values. So here's 1/2, here's 3/4, here's 1. Okay, so this is 1/2, 3/4, and 1. We'll just do it that way. Okay, so what it's telling us here is that this slope right here from 1/2 to 1, that's got a slope equal to, what was it, -2. From 3/4 to 1 looks to be a slope of -4/3. And then as we get this tangent line, right, this tangent line to the function at x equals 1, that slope equals -1. Okay, so the green and the blue are both secant lines. The purple would end up being a tangent line. All right, let's move on. Okay, find the average rate of change of the following function on the interval 0 to 2. Well, to find the average rate of change, we're just going to take f of the upper minus f of the lower over x value minus x value. So f of 2, well, that'd be 2/3 2. Now watch what I'm going to do. I'm going to cube it and take it to the 1/2 power, right? That'd be the 3/2 power minus the same thing, but I'm plugging in 0, which clearly would be 0. So f of 0 would be 0, and that'll be all over 2. Let's clean this up a bit. That would be, looks like 2/3 the square root of 8. So 2 cubed is 8, and to the 1/2 power would be the square root. That over 2. These 2's will cancel, and then I think I can do a little bit of simplifying. Square root of 8 is the same as square root of 4, square root of 2. Reducing radicals should be a skill you have at this point. And it looks like I get that. Let's see if we got that as a possible answer. 2/3 times root 2, yes we do. That would be C. All right. What is the instantaneous rate of change of f of x equals x at x equals 5? You don't need to do a whole lot of work here, okay? You can if you want, but in this case, all I need to do is understand what the function is. Okay, f of x equals x is a line. And that line has a slope of 1 everywhere. So that includes when x equals 5. So what would be the slope of the function when x equals 5? Well, the instantaneous rate of change would be 1. So instantaneous rate of change would equal 1. All right, let's look at an application. Okay, this is interesting because now we're taking it from just position. We were going position to like a speed or a velocity before, but now we're going to go from velocity to acceleration. And the change in velocity is the acceleration. The change in position is the velocity, so it kind of piggybacks on it. So we're going one level up. So if I want the average acceleration, I'm looking for the change in velocity on some interval. So in this case, it's going to be, what do I want? I want the average acceleration of a rocket A over the interval from 0 to 80, indicating units of measure. Okay, so what I want basically is I want the velocity at 80 minus the velocity at time 0 over that interval change. Okay, so let's check out our values here. Here's my velocity at 80. Here's my velocity at time 0. So I'm going to take 49, which is feet per second, minus 5 feet per second over 80. And 49 minus 5 is 44. And that can reduce then to 11/20ths. Now this is where units get interesting. So velocity is feet per second. So acceleration is feet per second, or feet per second squared. So it looks like the acceleration is positive, meaning it's speeding up. Okay. So there you go. Acceleration will be units per second squared. Okay. Last example for today's notes is find the average rate of change of f of x on this interval from -4 to 0. So I want to go from wherever the function is at -4 to wherever the function is at 0. I want to identify those points. And then I want to find that rate of change, average rate of change. So I'm just going to take the slope between those 2 points. So I'm going to take f of 0 minus f of -4 over 0 minus -4. And this will give me my average rate of change. So f of 0 is -2. F of -4 is 0. 0 minus -4 is 4. Looks like I get -2/4, which is -1/2. That's your average rate of change of that function on the interval from -4 to 0. Hope it went well for you. We'll see you next time.